Well, everyone, due to the technical problem, we'll start in maybe 3 minutes. Other students will come back here. Okay, can you hear me? Yes? Okay, so first of all, sorry for inconvenience due to the miscommunication with TA. We made another room, so we will start here today. Yeah, maybe some of you are still coming. Okay. Right. So, okay. So as we announced to you, we finished your midterm. So we uploaded your midterm score. So total score was 92, and mean score was 57, and median score was the 59. And if you want to check your answer sheet, please visit our lab, Science Level Building 309C or 309T from 3 p.m. to 5 p.m. in May 11th or 10 a.m. to 11 a.m. in May 12th, right? Yeah. If you have any question, our TA will help you to understand or to check your answer sheet. So please visit. Okay. Any question Are you satisfied? No? Yes? Right. So we have a final exam. So let's study further. Okay. Any other question? No? Right. So okay, so by the midterm exam, we studied how to solve your linear how to formulate your linear system, especially Ax equals b, and we discussed how to determine the solution of your linear system and how to solve this one, right? And the remaining part in this semester, we will talk about how to understand your first of all, how to systematically solve your linear system. For example, least square solution or something like this, which is one of the most efficient technical way to solve your linear system. And then we will definitely understand the effect or the just effect or the action or other phenomena by using the matrix multiplication AX. Then we will talk about how to decompose your matrix A to the other matrix, something like the eigenvalue decomposition or the singular value decomposition. Okay. Right. So today we will talk about inner product, length, and orthogonality of the matrix or the vector. Okay. Okay, so this is chapter 6.1. 6.1. We move to the chapter 6, the product, length, and orthogonality. Okay, so first of all, we have to talk about inner product. The concept of inner product is one of the most popularly used technique to say similarity between vectors. For example, if you have a vector u and vector v in Rn space, and then we regard u and v as n by 1 vectors, right? N by 1 vectors. So, for example, vector u is kind of u1, u2, un, and v is kind of v1, v2, vn. And because this is kind of the matrix, we can define the transpose of vector u transpose, as a 1 by n matrix, 1 by n matrix. So which is defined looks like this: u1, u2, un, right? And matrix product u transpose times v is a 1 by 1 matrix, right? Why? U transpose is n by 1 vector, and v vector v is n by 1 by n and n by 1, then it's going to be n 1 by 1 vector, 1 by 1 matrix, right? Which you write as a single real number, right? Then the numbers U transpose v is called inner product of U and v. It is written as U dot v, inner product of U and v, which is written as U dot v. The inner product is also referred to as dot product, inner product or dot product. It's a definition. So looks like this. For example, okay, let's say we have a vector u and vector v. Then it's going to be u transpose v, and u transpose is going to be u1, u2, let's say n times v1, v2, vn. Then by the rule of the matrix multiplication or the vector multiplication, it's going to be the 1 by 1 vector, 1 by 1 matrix, so which is just scalar value. Then this vector times this vector, right? So it's going to be U1 V1 plus U2 V2 plus UN Vn. Okay, so which is the dot product or inner product of matrix or vectors. Okay, so here's examples. Here's example. So U V and U dot V is going to be U transpose V, which is inner product, and U is looks like this, V is looks like this. So U V is going to be looks like this, right? So for example, let's say vector U is 2, -5, 1, and vector V means vector V is defined like 3, 2, -3. Then inner product between U and V or U and V or U dot V is going to be U transpose times V transpose, which is equal to 2 times 3, -5 times 2 plus 1 times -3. It's going to be 6, -10, -3. It's going to be -7. So inner product of U and V or between U and V is going to be -7. So this is very simple example. Okay, this is inner product. Question? No? Okay, it's very, very easy. So here is just one of the theorem for the inner product. Let's say U, V, W be the vectors in Rn space, and let's C be a scalar. So in this case, there are 4 kinds of property. First of all, U inner product times V inner product. U dot V is equal to V dot U. And U plus V dot W is going to be U dot W plus V dot W. CU times, not times, CU dot V is equal to C times U dot V, inner product U and V, and which is equal to inner product, U inner product CV. And U inner product U is greater or equal to 0, and U dot U is equal to 0 if and only U is equal to 0. U is equal to 0. Let's prove this theorem. It's a very, very theorem. You can do that. First of all, for the first theorem, first statement, we can easily prove this one. U V was U1 V1 plus U2 V2 blah 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 UN Vn, and V the product V inner product U is going to be V1 U1 V2 U2 Vn Un. So we already know each term are equal. So these 2 statements, left hand side and right hand side equation is equal. So we prove this one. Similarly, you can prove second one, third one, or first one, right? So which is going to be the homework. So please derive this or prove this each statement by yourself. Okay, it's very easy. You can do that. Looks like this. So this is the inner product theorem. Properties B and C. Properties B and C. This one, 그렇죠? Property B and C can be combined several times to produce the following useful rules. Looks like this. C1 times U, vector U, plus C2 times vector U2, plus CP times vector UP times W. Times W equals to C1 times U1 inner product W blah 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 CP times UP inner product W. So from this one and this one. So we can derive new statement. Looks like this. So first of all, what is this? we already saw so many kinds of this equation. C1 times U1 plus C2 times U2, CP times UP, blah, blah, blah. What is this? Anyone? 자, linear combination, right? Linear combination of what? 뭐죠? Linear combination of vectors, right? U1, U2, and UP. So, otherwise, we already discussed the whole possible vectors of linear combination of vectors. So we call this one as a what? Span, right? So span. So from here, we will see this kind of inner product can be used to solve A equals B from here. So let's see later. Okay. Anyway, so this is the definition of the inner product. It's very, very easy and it's very, very important and it's very, very fundamental and essential operation. You have to know. 뭐 이거는 중요성은 너무너무 간단하지만 아마 여러분들이 말했지만 컴퓨터 사이언스에서 벗어나지 못한다면 아마 무조건 알아야 되는 오퍼레이션 중 하나가 바로 이너 프로덕트예요. 뭐 더하기 빼기처럼 써야 되는 게 바로 이너 프로덕트라고 봐도 과언이 아닐 정도로 너무 중요한 거지만 너무나 쉽고 하지만 너무나 당연히 알아야 되는 이제 바로 이너 프로덕트라는 거죠. 알겠죠? 질문. So, first question is why do we have to know that? Why do we have to study inner product? And why where do we use this inner product? First of all, we can define length of the matrix or the length of the vector by using the concept of the inner product. So, first of all, length of the V or norm of the V, length of the vector V is a non-negative scalar defined here, which is defined by length of the V is equal to square root of V inner product V or inner product V and V, which is equal to square root of V1 square, V1 square, V2 square, Vn square. In other words, the square of the length of the vector is going to be the inner product of the vector of V and V. So this is the definition of the length of the vector V, right? So we already know this one from our middle school or high school, right? So, okay, let's go back to our middle school. Okay, so here is the one of the vector, let's say 2,3. Then what is the length of this vector? What was the length of this vector? What was the length of this point? It was 2 square plus 3 square. 그렇죠? Square root of the 2 square plus 3 square, which is one of the examples of length of the vector, because this is a vector, right? And here we generalize this one as a n-dimensional vector. N-dimensional vector looks like this. So we have to define inner product V times V. Let me show you example. Let's say vector V is 1, 2, 0, and then the length of the V is equal to square root of vector V dot V, which is equal to square root of 1 square plus 2 square plus 0 square, which is equal to square root of 5. Then the square of the length of the V is equal to 5. Why? From here. So from here. So square of this one is going to be 5. So square of length of the V is equal to 5. Yeah. Okay. So from now we can say that each vector have a length. Then we can find out length of vector looks like this. So, any question? Any question? Right. So suppose V is in R2 space. I already show here. 그쵸? Let's say V is in R2 space. Let's say vector V consists of the A and B. If we identify V with a geometric point in the plane, 그쵸? 이렇게 here A, B, then length of the V coincide with the standard notion of the length of the line from the origin to V. This one. 그쵸? This follows from the 피타고라스 theorem, 그쵸? 피타고라스 정리죠? In Korean, 그쵸? Applied to the triangle. Because the length of this one, length of the line from the origin to V can be determined by length of this one and length of this one, which is the length of A and length of B. So, which is going to be square root of A square plus B square. So, which is the length of the vector V. If we define vector V as A, B. Okay, so this is length of V. Very easy, right? This is length of V. And for any scalar C, the length of C times vector V is length C. This is just like absolute value of the C times length of the V. That is length of the C times vector V is equal to absolute values of C, because this is a real value, times length of the vector V. So here's the example. If there is vector V, looks like this, and length of the CV, let's say CV is here, or if C is larger than 0, or maybe here, if C is smaller than 0, then length of this one, CV, or this one can be absolute value of C times length of the vector B. This is the definition of the C times length of the C times vector B. And one more thing is that a vector whose length is 1 is called unit vector. For example, if our vector U define 1, 0, then the length of the U is equal to 1 y square root of the 1 square, which is equal to 1. Then we call this one is unit vector. This is one of the examples of the unit vectors. Okay, this is unit vector. And if we divide non-zero vector V by each length, let's say, looks like this. That is multiply by 1 over length of the V, 그렇죠? Divide by니까 multiply by 1 over length of V. We obtain the unit vector U, because the length of the U is always here, which is equal to 1. So we can make a unit vector U by dividing a non-zero vector V by its length of the V. Any question? So which is the example? Here's the example. Let's say vector U, vector V is defined like this. And if we normalize, if we divide non-zero vector v by its length. Let's say new vector u is going to be vector v over length of vector v, length of vector v. Then this vector is called unit vector. Any question? By the way, is there anyone who heard about length of the vector or the inner product? Anyone? 자, 제가 좀 빠르게 넘어오고 있는데 혹시 이런 이너 프로덕트나 뭐 벡터의 랭스라든지 이런 개념에 대해 처음 들어보는 사람? 그러면 많이 들어봤다. 예담 학생. Any others? 못 들어봤다고. 네, 그 다른 친구는 어때요? 처음 들어봤어요? Other? Okay, that's fine. But fine so far. But from now on, you have to know that. You have to know that because after this semester, if you take a advanced course, most professors will just assume you already very well know of this kind of concept. Okay, so please be the master of the vector here or matrix. Okay. 아마 여러분들 이거 지금 제가 항상 이렇게 물어보는 이유가 아마 이제 여러분들이 전산 수학을 끝나고 다른 수업들로 넘어가면 다음 학기 뭐 그 다음 학기 들어가면 너무 당연히 모험 확률과 통계부터 해가지고 너무 많은 수업들에서 너무 당연히 이런 컨셉들을 안다고 넘어갈 거예요. 교수님들이 아마 여러분들이 무슨 수업을 들어도 그 이유가 조금 뭐 복잡한데 예전에만 해도 이런 개념들이 사실 고등학교 때 다 배웠었기도 했었고 여러 가지 이유가 있긴 한데 그래도 아무튼 전산 수학이 그래도 중요한 거긴 한데 그렇기 때문에 여러분들이 완벽하게 알지 못하면 계속 헷갈릴 거예요. 맞죠? 그래서 So finally, if you have any question, if you have any question, please let me know now and in this semester. 그래서 여러분들 아마 이제 이런 컨셉들 제가 항상 얘기했지만 모르겠으면 여기서 알고 가야 돼요. 정말. 알았죠? 이게 왜 하는지 알겠죠, 여러분? 전산수학 시험 점수를 보고 열심히 해야겠다는 생각이 많이 들었어요. 그쵸? 알아야 돼요. 여기서 알아야 돼요, 여러분. 진짜 알아야 되고 모르면 지금 물어보세요. 알았죠? Okay. So, the first question is the 분모에는 No. So, question was this notation is necessary to represent the length of the V? The answer is no. We have to. This is just the definition of the length. So we have to know that. And we have to represent this one every time. 분자. 분자? 어디요? 예담학생 분자에 어디 이게 있지? So yeah. So you mean this one? This is vector, and this is scalar, right? It's totally different. PPT? 이거 말하는 거 아니에요, 예담학생 여기? 그쵸, 그쵸. 완전 달라요. 이건 벡터예요, 지금. 이거는 지금 다른 색깔로 합시다. This is vector in our n space. For example, this is color in our space. So U is also vector, right? So here, this is just a vector. It's not a scalar. It's not a length of the vector V. Okay. Any other question? No. Then maybe you have question here. Why do you have to know that? Then I want to give very simple examples here. Let's consider the three-dimensional space. Let's say R3 space. And let's say there are three kinds of vector. V1, V2, maybe V3. Then let's discuss relationship between V1, V2, and V3. Let's talk about similarity between V1, V2, and V3. So question is, V1 similarity between V1 and V2. Let's say similarity between V2 and V3. Which one is more similar? I mean, let's say vector V2 here. The question is, V1 is more similar to the V2 is more similar to the V1 or more similar to the V2. Otherwise, V2 is more similar to the V1 than V3. 자, 무슨 하고 싶은 거냐면은, 자, V1, V2, V3 이렇게 있어요. 자, V1, V2, V3를 봤을 때, 이 V1, V2, V3의 relationship. 자, let's say relationship. 을 결정을 내려는 순간이 정말 많아요, 이제. 관계, similarity. 자, V2는 V1, V3 중에 어디와 더 시밀러 할까요? anyone? V2라고 하는 벡터가 이렇게 있을 때 각도의 의사성 이거 많이 나갔네요. 그쵸? 연관이 있어요. 정학생. 그냥 좀 더 일반적으로 얘기해봅시다. V2가 어떻게 생겼을 때 V2를 그냥 딱 놨을 때 V1과 V3와 어떤 벡터와 더 가깝다고 할 수 있을까에 대한 얘기를 해야 되는 거예요, 지금. 자, 정학생은 답을 알고 있는 것 같아서 벌써 얘기를 해줬는데, so to determine the similarity of the vectors, we have to consider not only length of the vector, but also we did not discuss the angle yet, so we will forget the angle. Then when we determine relationship of the vectors, the length of vector is not a solution, right? Maybe in terms of the length, V1 and V2 is more similar than V2 and V3. But we can assume this vector is more similar to this one because the direction of the vector are similar than V1. Then how can we determine the similarity of the vectors? That's the point of the inner product or unit vectors. Otherwise, if we consider unit sphere, let's say unit sphere. Unit sphere means each vector in this space has the length 1. So unit sphere consisting of the unit vectors. Then we can normalize each vector V1 and V2 and V3 to the unit sphere. For example, U1, U2 and U3. U3. So for example, U1, it's going to be vector V1 over length of the vector V1, right? U2 is equal to U2, vector U2 over length of the U2, and U3, it's going to be V죠? V2, V3 over length of the V3, length of the V3. So again, the question is similarity between U1 and U2 versus similarity between U2 and U3. What can we do? So how can we determine the similarity between U1 and U2 or U2 and U3? So in this case, we can easily say that U2 and U3 are more similar than U2 and U3, U2 and U1 in unit sphere. That's the concept of the inner product. That's a concept of the inner product. 자, 이 부분 중요하니까 한 번만 더 설명을 해줄게요. 뭐 뒤에서 조금 더 당연히 얘기를 할 거긴 한데, 자, 우리가 이제 요 이너 프로덕트라고 하는 걸 지금 왜 얘기를 하고 있느냐? 결국에 이 similarity, 벡터들 간의 similarity를 얘기하고 싶어서예요. 벡터들 간의 similarity. 그러니까 우리가 지금 보면 뭐 어떤 스페이스 안에 R3라는 스페이스 안에 뭐 V1, V2, V3가 있을 때 V2와 V3가 더 유사한지 또는 V2와 V1이 더 유사한지에 대한 얘기를 해야 되는 문제가 정말 많아요. 그렇죠? 이제 우리가 뒤에서 또 얘기할 게 어디서 얘기를 해야 되는지. 근데 그럴 때 어떻게 얘기를 할 거냐? 뭐 길이가 비슷하고 비슷할 거냐? 그러지 않을 거라는 거죠. 그러니까 그러지 않은 경우가 많다라는 거죠. 결론은 뭐냐면 이 두 개의 시뮬러리티를 얘기할 수 있는 가장 좋은 방법은 V1, V2, V3를 어떤 노멀라이즈라고 표현할 건데 앞으로 유닛 스피어로 보내서 유닛 벡터로 보내서 유닛 벡터들이 얼마나 유사한 방향을 보고 있는지를 보는 게 벡터들 간의 거리, 벡터들 간의 시뮬러리티를 결정할 수 있는 가장 정확한 방법이다 라고 알려져 있어요. 그렇기 때문에 이제 이런 우리가 그 노멀라이제이션, 뒤에 얘기할게요. 유닛 벡터스, 그 다음에 이너 프로덕트라는 얘기를 하는 거고, 결국에 나중에 finally we will talk about similarity of the V1 and V2 can be represented by dot product of inner product of V1 and V2, and similarly V2 and V3 is going to be the inner product of the V2 and V3. 이걸 내가 싶어요. 그래서 결국 이너 프로덕트라고 하는 거는 결국 벡터 사이의 거리를 표현할 수 있는 방법이다. There are so many kinds of distance measure to determine similarity between vectors, but this kind of inner product is one of the most simplest one and the most efficient way to define the similarity of the vectors. 그래서 가장 간단하면서도 가장 효과적인 매트릭이 바로 similarity를 잴 수 있는 방법이 바로 이 inner product다 라고 하는 거예요. 그렇죠? Question. So in this here, okay. So in this regard, the processing of creating the vector U, unit vector from the vector V, is sometimes called normalizing V. Normalizing V. We will call from now on this process as a normalization of the vector V to the unit vector. Normalizing vector V. We say U is in the same direction as V. Here, 그렇죠? Same direction, but with different lengths. Here, unit vectors U1, U2, U3. This is concept of inner product and unit vector. Any question so far? No? Okay, so before going deeper, I will give you very simple example how to compute length, how to compute unit vectors u given vector v, arbitrary vector v. So this is the definition of the unit vector. Vector u equals to v over length of the v. So we have to, first of all, we have to compute length of the v. So square of length of v is equal to vector v inner product vector v, which is equal to this one. Square of the first term, second term, third term, fifth term, first term, square 2, square 1, square of -2, this one, which is equal to 9. So we say that length of the vector v is 3, right? And then vector u is going to be the 1 over 3 times vector v. So vector v also looks like this, and finally u is equal to looks like this, right? So this is the unit vectors of the vector v. How to prove the answer is correct? We can easily compute the length of the vector u, which is equal to square of the 1 over 3 plus square of the -2 over 3 plus square of the 2 over 3 plus 0 square, right? If you compute this one, which is going to be 1. So length of the u is equal to 1, so u is a unit vector in the same direction as v. See, in the same direction with v. Same direction with v. Okay? Any question? Any question? Nope. Okay. Okay, let's go further. Then we have to introduce one more concept, distance in Rn space. Distance in Rn space. For any vector u and v in Rn space, distance between u and v written as distance u v is the length of the vector u minus v. Let's say vector u is here. Let's say vector u is here and v is here. Then the length of the v, distance of the u and v, 거리죠? 벡터 u와 벡터 v의 distance는 length of the u minus v. Length of the u minus v. So how to compute the u minus v? This one, which is vector u minus v, 그렇죠? u minus v. Then length u minus v means length of this line. Length of this line. This is the definition of the distance between u and v. vector u and v. 이제 우리가 어떤 벡터 u와 v의 디스턴스가 얼마냐 라는 얘기를 할 때는 이 둘 사이의 거리, 결국 이 둘 표현하는 어떤 라인의 랭스로 표현할 수 있다라는 거죠. Very simple. And here's example. Let's suppose vector u is 7,1 and vector v is 3,2. Then u is 7,1 and v is 3, let's say 3,2. Then distance between two vectors is going to be the length of this red line. Length of this red line. Then how to compute this one? So first of all, calculate u minus v, which is going to be 4, -1. Then length of the u minus v is going to be the square root of the 4 square negative 1 square, which is going to the square root of 17. Then when the vectors u minus v is added to v, the result is u. It means that, let's say u is here, v is here, u minus v is here. The length of this one is equal to length of here. So length of the u minus v is going to be the distance between u and v. Then, in other words, distance from u to v is the same as the depth from the u minus v to 0. 그거 뭐 이게 무슨 얘기냐면 뭐 어려운 얘기 아니고 그냥 이 u와 v 사이의 디스턴스는 요 거리, 요 둘 사이의 벡터 거리인데 요 둘 사이를 나타내는 라인의 거리인데 그건 뭐야? u 마이너스 v를 이렇게 원점으로 표현했을 때 요 거리가 똑같다. 그렇죠? by the parallelogram rule. 평행사변령 때문에 당연히 그런 거죠. 그렇죠? 그래서 그렇게 표현되더라 라고 하는 거죠. 됐죠? Any question? So this is a way to measure the distance between vector u and v. Maybe there will be some relationship between inner product and distance of vector u and v from here and here, maybe, right? Then let's talk about what is this, okay? 아마 그래 여러분이 여기까지 얘기했으면은 아까 제가 계속 벡터 간의 similarity를 얘기하는 게 그렇죠? 이너 프로덕트라고 했고 뭐 one of the most simplest way to 그러니까 메트릭이라고 했는데 또 이렇게 그냥 distance라고 하는 거는 u-v의 어떤 랭스로도 표현이 된다고 하는 거죠. 그렇죠? 뭔가 연관이 있는 것 같죠, 둘이? 그렇죠? 조금 더 얘기를 해봅시다. Then we'll talk about one more concept, orthogonal vectors. Orthogonal vectors. Consider R2 or R3 and two lines through the origin determined by u and v. Let's say vector u is here and vector v is here. Then two lines are geometrically this one, two 라인이 그쵸? This line and this line are geometrically perpendicular. 직교, 그렇죠? 한국말로 in Korean 직교. If and only if the distance from u to v, distance from u to v, this one is the same as distance from u to negative v. So maybe negative v is here, and length of the distance from u to negative v is going to be the here. And if these two lengths, these two value, length of the u minus v and length of the u minus v is equal, then we call vector u and vector v are perpendicular. So this is the one of the definition. Then we can represent this one in our minuscule way. Looks like this. Vector v and vector u are perpendicular. Or orthogonal. Then u and v are orthogonal. Or u and v are orthogonal vector. This is definition. Question. 자, 혹시 여기까지 질문? Question. Today we just introduced some terminology and the some notation, right? This is very easy, so you just memorize what I mean. So question by 정우. So interesting. This is definition. This is just definition of the orthogonal vectors. So we can say the two vectors are orthogonal if and only distance from u to v is same as distance from u to negative v. So this is a kind of property, but this is definition. Okay. Question. Then let me show you in detail. So to vector to make other two vectors u and v orthogonal or perpendicular, the u minus v, length of u minus v should be equal to length of u minus negative v. Looks like this. Then let's solve this one and this one independently. So first of all, this one, distance u negative v, 그쵸? Here, 그쵸? is equal to length of square of length of u minus v, which is equal to length of square of u plus v, which is equal to u plus v times u plus v dot u plus v, inner product of u plus v and u plus v. Then by the properties of the inner product, which is going to be u times u plus v, u dot u plus v, u dot u plus v, and v dot u plus v, v dot u plus v, which is equal to u dot u dot v, v dot u, v dot v, which is equal to, this is the length of the v, square of the length of v, which this one is the length of the v2, and these two terms, it's going to the 2 u dot v, 2 u dot v. And from the left hand side, distance of u and v is going to be the similarly square of the length of the u, square of the length of negative v, and plus 2 u inner product negative v, which is equal to, looks like this. Look like this. So first of all, to make these two terms equals from here, so this one is equal and this one is equal, and these two terms should be equal. I mean 2u v should be equals to negative 2u v, right? To become perpendicular or orthogonal vectors, 그렇죠? Then two square distances are equal if and only if 2u dot v equals to negative 2u dot v, which happen if and only if, when does it happen? If u dot v is equal to 0, or u transpose v equal to 0, or inner product of u and v, or dot product of u and v is 0, then vector u and v are perpendicular. This is very, very easy. This calculation shows that when the vectors u and v are identified with a geometric point, then corresponding line through the point and original perpendicular if and only if u length, the inner product of u and v is equal to 0. In other words, if U is here and V is here, if U and V perpendicular, then U inner product V is equal to 0. It means that looks like this. 직교한다. 그렇죠? 그래서 두 벡터의 이너 프로덕트가 0이면 직교한다 라는 거고, if let's say here's another vector W, if U W is not perpendicular, then inner product U and W is not 0. So maybe the angle between vector U and W are not equal to 90. Let's say 90 degree. Not 90 degree. It's not perpendicular. I mean, vector U and vector W are not perpendicular and not also. So from here, we will derive very important definition here. Two vectors U and V in Rn space are orthogonal to each other if inner product U and V is equal to 0. Orthogonal or perpendicular. 그래서 이제 우리 무슨 얘기를 할 거냐? Okay, so let's say you have arbitrary two vector U and V, and if you want to measure the angle between U and V, but if we compute inner product between vector U and vector V, and which was equal if the inner product U and V was the 0, then vector V U and V are orthogonal. We can say the U and V are orthogonal. That's the very important theorem, even though it's very simple. Okay? 그게 뭐예요? 우리 다시 얘기하면, 그래서 어떤 벡터 두 U와 V가 있어요. 이게 왜 중요한지 계속 우리가 볼 거야. 근데 두 벡터 V, U와 V가 inner product 0이에요. 그러면 두 개의 벡터 U와 V는 orthogonal하다. 직교한다고 말로 perpendicular하다 라고 할 수 있다는 거죠. 너무나 중요한 theorem, definition이에요. 우리 앞으로 쓸 거예요, 이걸. 알겠죠? The one more thing is that the zero vector is orthogonal to every vector in Rn because the zero vector times V is equal to 0 for all vector V. So zero vector is orthogonal to every vector. 뭐 당연한 얘기죠? 그렇죠? Question. So by using this kind of concept, we will reformulate Pythagoras theorem and angles of the vectors, and we will talk about how to measure the similarity between the vectors, then which can be so many kinds of application. Distance in deep learning or the loss function in deep learning is one of them. So next lecture we will talk about why do we have to know the distance between two vectors, or the length of or similarity of these two vectors, and how can we use this kind of concept in orthogonality theorem or the orthogonal orthogonal decomposition method to analyze your matrix A. 그래서 이제 오늘 뭐 여러 가지 우리가 얘기를 했었고, 결국에 뭔 얘기하고 싶다고 했냐면은 어떤 벡터들 간의 디스턴스 or similarity들을 재고 싶을 때 어떻게 잴 수 있을까 얘기들을 쭉 해오고 있어요. 그래서 이제 이게 사실 너무 많은 곳에 쓰일 수가 있고, 이제 어디에 쓸 수 있는지 다음 시간에 좀 얘기해보고, 이제 이걸 이용해서 요 다음 시간에는 어떤 orthogonal set, 우리가 지금까지 linear independent set이라는 걸 정의를 내려봤죠. 근데 거기서 조금 더 나아가 orthogonal set이라고 하는 걸 정의를 내리는 것들에 대해서 얘기를 해보겠습니다. Question. No? Okay. So this is the end of today's lecture. Sorry for inconvenience. The starting point, starting of today's lecture. Sorry about that, and thank you very much. And let's see. 우리 언제 보죠? 화요일. 그죠? Thursday. 오케이? 여러분 오늘 너무너무 수고했고요. 우리 아까 저희가 좀 조교님이랑 조금 미스테이크가 있어가지고 준방이 좀 혼동됐던 거 미안합니다. 그다음에 우리 중간고사 성적 공지됐고요. 그 중간고사 시험 지역이라는 친구들 공지됐죠? 내일이죠? 수요일날 3시, 5시 또는 목요일날 10시, 11시 사이에 조교님들 찾아가면 되고요. 혹시 더 궁금한 거 있거나 시간 안 되는 친구들은 저에게 따로 연락 주시면 됩니다. 알겠죠? 네, 그러면 오늘은 여기까지 합시다. 여러분 고생 많으셨습니다.